Hi class, welcome back. So now what we're gonna do is we're gonna go jump into linear regression. Is this the correct one? I think so. Oh, there you go. So we'll click on linear regression for the second PowerPoint. So let's click on that one, and we're gonna see the first model of machine learning, which is linear regression. I think is the easiest one to understand. If you haven't seen if it's not uploading, then you can just click download and you can just open it through there. And let's open the whole PowerPoint instead. So the first model that we're going to talk about is linear regression. I think it's the easiest one, but it still requires some mathematical concepts, right? Remember in the graph for machine learning, we said that machine learning usually does require mathematics like linear algebra, calculus. And if we go into higher graph theory, so we're gonna talk about some of those concepts. We're not gonna go too heavy in the math because we wanna make sure we focus on the model and not on the mathematical part, right? And again, this most of the mathematical part is done in it's called SCI Kit Learn, which is a Python library. So let's talk about the objectives. Regression, linear. What does regression mean? Linear regression, prediction versus inference, evaluating a linear regression. Okay, so let's talk about this, and that way we can have an understanding of what linear regression is. So, like I mentioned before in the PowerPoint, there's three different types of learning: supervised learning, unsupervised learning, and reinforcement learning. We said that supervised learning is kind of like when you're given uh, it's like imagine that you have all these emails and you want to be able to determine. So that's the data, that's the experience, and then you have a task. The task is to determine if your email is a spam or legitimate, and then performance is to determine how accurately did your machine model did. So in this case, when we do supervised learning, uh, well, let me give you the definition. The computer is given the data and the programmer asks the model to determine the relationship between the input and the output variables. Okay, so going back to the example. So now you have all these emails and you want to train the model. So this is going to be a supervised model. So what you do is you have the answer already. So you have the email and you already know that this is spam or a legitimate email. So by having that information, you're gonna tell the computer what is good and what is and what which one is the good email and which one is a bad email. So from that, it's gonna learn. So you're actually helping, you're supervising the learning of the machine, and hoping that after that, then the machine will be able to determine if an email, a new email will be coming up is a spam or a legitimate, and then determine the performance, right? So that's supervised learning. You're helping the computer learn by itself with your help, right? Unsupervised learning is when you just give them all the emails, and the computer has to find a pattern, and hopefully it will be able to determine that there's a group of emails that have a pattern, like for example that they are legitimate and the other ones are not. So you're hoping that the computer will find that, determine that pattern, or that your machine will determine that there's a pattern between good emails and a bad email, spams versus legitimate. So that's what it's provide. You're not telling them that this is a spam and this is a spam email and this is a legitimate email. That's unsupervised learning. Okay. So let me give you the definition. The computer is given the data with no direction from the programmer, and the computer finds hidden patterns. Now, reinforcement learning is a model that improves upon itself in a new situation using a trial and error method, very similar to how humans learn. So, for example, again with the emails, right? So the computer is gonna take an email and see if it's a spam or a legitimate. It's going to predict based on the information that is given, and if it is if correctly predicts that it's a good email, a legitimate email, it's gonna continue. It's gonna learn from that, and if it's wrong, it's gonna learn from that mistake. It's gonna determine why did it not able to determine that it was a spam. So that's kind of like similar how humans do it, right? We try things, and then based on if an error, right, we learn from it, we adjust. Here, there's two, in supervised learning, there's two different types of data and two main tasks. So there's regression and classification. So a regression tries to fit data. It seeks to understand the relationship between dependent and independent variables. So regression is more continuous data. When you have a continuous data, you're gonna use regression. It's kind of like, for example, the the house price in a community, right? So you're gonna get all these houses depending on the area, number of bedrooms, the square footage, and based on that information, you're gonna be able to predict what the price of the house will be, right? So that number, right, that you're trying to predict, that's your target label, and what you're in that label values, those values are continuous. So it could be 300,000 as a price, right? Or it could be 299,999, right? So it's a continuous value. So when you're thinking about continuous values, you should be thinking of regression. If you have a classification, that means that your supervised learner is going to try to split the data. It seeks to accurately assign data to different categories. So what does that mean? It means that it's either it's discrete, what we call discrete data. So what does that mean? It means that for example, it could be like it's a cat or not a cat, or a cat or a dog, or a cat, dog, or a bird. So where it's not that, where the actual prediction is not continuous. It's like it's you already know what kind of type of item would that be. So when it's not continuous, it's going to be a classification. Okay. So that's practically how you want to see it. Regression would be continuous, classification would be non-continuous. We call them discrete. So here is other examples, right? So regression would be an example, would be a linear polynomial regression. So as you can see, a linear equation would be continuous. A logistic regression can be a classification, and so a logistic regression will be able to help you separate a group of labels, like it could be a dog, a bird, or a cat. K nearest neighbors can be used for both, and deep learning can be also used for both, for linear regression and classification. So so the first one is the first picture in the middle is what we call logistic regression, and then we have the k nearest neighbor, how close they are. We'll talk about k near neighbors in deep learning as well. So you can see the different layers in deep learning. We'll talk about that as well. In supervised learning, the label determines the task. So again, the label is what you're trying to predict, the column that you're trying to predict. So we usually call them labels, or we call them your target, right? Your target column. So I'm gonna use those often. So if the label is a continuous number, then it is regression. So here we can have a couple examples to determine if it's regression or classification. You want to predict the specific stock price in the future, that's going to be regression because continuous values, right? The label will be continuous. You want to determine when a house prices will be the lowest to buy, regression, that can be continuous because time is continuous. You want to know if a training program is making a runner faster, that's classification, right? It's either doing it or not, right? It's either making it faster or not making it faster. You want to guess the average temperature of different places shown in images. That can be classification. It can also be regression, but we can do it because we can say we can have just specific temperatures, like maybe 80 degrees, 90 degrees, 100 degrees, 101, 10 degrees. So if we have something like that, then that will be a classification. But if we are actually talking about a specific any range of temperature, then that will be a regression. You want to determine if the average temperature based on the zip code, right? So that will be regression. We can do, like I said, you can be regression or classification depending on how your label values are set up, right? If it's 80 degrees, 90 degrees, 100 degrees, 110 degrees, and that's a classification because there's nothing in between, right? We cannot have like 95. So that means it's not continuous. It's just a classification. It's either one or the other ones. So then that could be a classification. Or if you actually have every single value on temperature, then that's a regression. That's continuous. So that's what I meant there. Data for regression models. Regression is a task of estimating the relationship between features and their label, also called their target. So I mentioned the word features before. So that features is used in your columns. Part of the data. Each row contains a unique data, and in that data it contains many different options of data. So for example, let's say that the first data, right, the first house contains that it's 10 years old. It has 1,910 square footage, has the number of windows is 8. So that has 3 different features, 3 different columns of data, right? Even though it's one row, right, one house, it has 3 different features, right? And what we're trying to predict is the price of the house. So that will be your label, your target. What is it you're trying to predict? What column are you trying to predict? So when you're training your data, you will have, you need to have, if you're going to use supervised learning, you need to have your features columns and your label column. So features can be categorical or numerical in regression. So when you're doing a regression model, you can have both of them. You can have categorical or numerical. Numerical means continuous, categorical be an option, right? So in this case, you can say that it is number of windows is 8, that's categorical because it's not continuous. You cannot have 8.00001 of a window. So what happens here is that you're gonna take this data, all these rows and data, and you're gonna put it into your regression, and from there it's gonna predict what it's gonna learn from your data, and it's gonna be able to predict what the value of your house should be. So the target variable must be numerical and continuous, meaning any numbers are allowed. So that's what it means. Again, regression means that the target value is that your label is continuous. Remember that. Remember that. Here are other types of regressions. We can have a simple regression where we only have one feature and one target. We can have multiple regressions, which is the one we just talked about, multiple features and one target, house size, location, gas price, and just predicting the house price as a label or target. So those are your column, that will be your column features, and then you only have one column target. In multivariable regressions is when you have multiple features and multiple target. Okay, very straightforward, I think. Key terminology when you talk about linear regression. The linear regression is a task of estimating a linear relationship between features and their labels, also called their target. In other words, linear regression tries to find the line that best describes the observed data. So for example, let's say that here we have a feature columns, political trust and happiness. So we're going to use that information to be able to create a relationship between political trust and happiness across the country, and it's going to be able to draw a line that that best fits that information. So that's what linear regression is. It's just a straight line. That's why it's the easiest one, because we know what a straight line looks like. It's y equals mx plus b, right? So now one of the most important questions and things that is hard to understand is that there's a difference between what we call an algorithm versus a model. And in machine learning. So in machine learning, an algorithm is different than a model. Okay, so have that in your mind. They're both different. An algorithm is not a model, and a model is not an algorithm. So let's talk about it in the sense of linear regression. So the algorithm is the program, is your program, what you have typed up and everything. And when you add data to your algorithm, when you input data, then you actually create a model. So an algorithm plus the data makes the model. So the model will be the output that would generate from the given the data on your algorithm. So for example, here the algorithm in linear regression would be whatever we have, cooked up to be able uh, to create this linear regression. The linear regression, after you put the data, right, and it takes the data and learn from it, and you're just gonna draw this linear line. That is the model. That vector, that y equals mx plus b, is the model in the end. So whatever got us to the y equals mx b vector line, whatever get us there, right? So the algorithm plus the training data is going to form the model. So the model is the linear vector. Okay, so the algorithm is just the program, right? So linear regression training algorithms, more on this later, right? So any kind of features and numerical continuous labels as a straight line. So the model is a straight line. We'll talk about it more before linear regression. So this is just the data, the training data, and then now after the linear regression, we now have a predicted linear equation. So the line best fits. Once we apply the linear regression tools, then we're gonna be able to predict a linear line, and then based on the training data. So that straight line is the model. So for example, here, a linear regression example, you're looking to sell your home and you know the square footage and prices of homes in your neighborhood that are sold recently. So here we have three different data. So we have the size and the price, and we're gonna put that in a linear regression to be able to predict what the house price would be. So the square footage and the price are set up together, and you place them on the graph, and you try to predict a line that goes through those points, and that will be your model. So whatever we use to be able to get to that model, whatever we coded, that will be the algorithm. So an algorithm is kind of like the like what we do. You might have seen maybe the algorithm for sorting methods. That is the algorithm, right? To sort your data. So that's an algorithm. So in here, the model is after you place your data. So once you place your data and learn from it, then you create the model. So just remember that. Just the algorithm by itself, without the data, the program without data is just the algorithm. So now after you have created and predict and fitted your or train your data, you can make a prediction now. So if you have a 1600 square footage house, you can predict what the price of your house would be. So according to this, if you have a 1600 square footage house, your house price should be close to $400,000, I think, somewhere around there, right? Here's another example of a linear regression. So we can have three different datas, and so we can have a lot of, in this case, a lot of data, but we have two two columns. The one of the features and the other one is your target, and you want to predict what will be the car weight of your. You want to predict. Well, let's see what we want to predict here. What will be the miles? Sorry, one of them is your weight, and the other one is your miles per gallon. You want to predict what will be the miles per gallon of your car, given a lot of data. So you create this. You give this information to your algorithm, and then it creates a model, your linear regression line, and then from there you can actually predict what the miles per gallon of your car will be if it is 3 tons. So in this case, if it is 3 tons, you can predict that the miles per gallon of the car will be close to 23 miles per gallon. So now, how does it do it? Well, now we're gonna look specifically into the algorithm, right? So what is the algorithm doing to be able to learn from it and make the model? So how's the line of the best fit determined? We start with the line and see how well it fits using the helpful set of numbers called the residuals. A residual is the difference between the specific data point and the model prediction for it. So this is how we start. So this is how the algorithm works. So imagine that you have a bunch of data. So you're given a lot of data, a lot of points. And the first thing it does is just gonna draw a line, just random line around the data. And what it's gonna do is going to start calculating the residual from all the points, from every single point to the line. So it's gonna calculate the height, the white difference, and is going to square it and then add it together. And it's going to try to see, based on that information, it's going to adjust the line until it finds the line with the smallest sum of residual. So that's what it is. So let me say that again. So it's going to start first by randomly choosing a line, and then it's going to go through every single point on the data, and is going to take the difference on the y value from the point to the line. That's going to be the residual, and it's going to square the difference, and it's going to add it together, and it's going to add it to all the residuals of the other points, and it's going to move the line until it finds the sum with the sum with the smallest value. So here's more information about that. So the line of the best fit is determined by the residual sum of the squares. The goal is to find the smallest residual of the sum of the squares. This is also known as the cost function, which measures the difference between the predicted and the actual outputs. So it's gonna try to move it until it finds the best, the smallest sum, which is the cost of the function, also known as cost of the function. Now we're gonna go a little bit mathy, but this is how the equation looks if we have multiple features. If we only have one feature, it's just gonna equal, it's gonna be just y equals mx plus b. That's if you only have one feature. But if you have multiple features, you're gonna have a couple of more mx terms. So you can see you have b1x1, b2x2, b3x3, and so on, all the way to your y-intercept. Your b0 is your y-intercept. So the features are going to be the x values values are gonna be coming from the features, and the coefficient and the y-intercept are going to be determined by the algorithm to create the line with the best fit. So the b1, b2, b3, and the b0s, right, are going to be determined by the algorithm when it best fits the points. So once it finds the sum with the smallest value, then it's going to choose those values, those b1, b2, b3, b3, all the way to b0, right? To be determined that's going to be the parameters of your linear regression. So the label is your y, what you're trying to predict. So you can see on the right side, the residual will be the actual value minus the predicted. So you can see that on the right side. So the residual I will be y I minus b0 plus b1 plus x. Times xi. I think that's I think that's fine. Actually, that should have been a I, not a b1, but an I. Sorry about that. And so then you're just gonna square those residuals, and whoever has the smallest value in the residuals, that will be your the best fit regression line. So mathematically, the goal is to find the coefficient that will minimize the cost function. For a general equation, this usually is hard, but with linear regression, it is easy. So that is the how it's done. Again, we don't need to we don't have to do all this math part because it's already done in your we already have the tools in the library of linear regression, so we don't have to worry about that. The pros and cons of linear regression. Pros is simple to implement, can be trained easily, and low computation power required, easy to interpret, well studied and understood by the many communities. Okay, so that's very easy to understand, not hard. We can actually make predictions, see why it's predicted that way. Cons is have difficulty capturing complex patterns, performs partially poorly with non-linear data. So if it's non-linear data, it's not going to be able to do good prediction. Performs poorly with highly correlated features. So if you have a lot of features, a lot of columns that are very correlated, it's not going to do well. Does not handle outliers well. So if there's a point on the graph that is very, very far, it's not going to do well. It's going to skew the data. Predictions versus inference. So this is one that is also hard to separate or understand. So prediction, the purpose of prediction. So prediction, the primary goal of prediction is to make accurate forecasts or estimations about future or unseen data points based on patterns learned from the historical data. So this is going to be what you're going to try to predict on your data, right? You're going to be trying to collect your data, choose your model, train your data, train your model, and then you're gonna use your model to predict your whatever thing that you're trying to predict, right? So that's your prediction. That's what you're trying. That's what prediction does. You're trying to predict or forecast what is going to be the cost of your house in the future. So methodology predictive models involves training a machine learning model on a labeled data set, historical data where both input features and target values are known. So like I said before, since we're doing supervised learning, your input features and your target values are going to be known. The model learns the relationship between the features and the target, and then it can make a prediction in a new unseen data. Examples: predicting stock prices, weather forecasts, spam detection, image classification, and many other applications where you want to make sure the prediction is based on the past data. So this is not just in talking about regression, linear regression, but we can be talking about any model. Inference. The purpose of inference aims to understand and interpret the relationship within the data, often to gain insights or make casual claims about how different variables affect each other. So this is more to understand the relationship between the features than the prediction of your model. So this is to understand. Inference is to understand the features relationship between them to have a better understanding of what you're going to predict. Methodology in inference typically involves statistical methods such as hypothesis testing, regression analysis, causal inference, and techniques. It tries to determine if there's a significant relationship between variables or features that strengthen of that relationship and whether it can be generalized to a broader population. Examples: determining whether a new drug is effective by analyzing the results of clinical trial, understanding the impact of marketing campaigns on sales, or studying the influence of education on income levels. So prediction, here's an example, right? You're looking to sell your home and you know the square footage and price of your home neighborhood that has sold recently. How much should you sell your home for? So that's going to make a prediction. Inference, you're an economist and have the data on countries' GDP, income inequality, unemployment rate, and life expectancy. You want to understand the factors affect life expectancy at the country level. So again, you're trying to understand more about the features, not about the predictions. So that's what the inference and prediction separate from. How do we evaluate our model? So how do we evaluate our linear regression? So the core linear regression metrics. So for linear regressions, we can use three different performance tools. We can use the R-square coefficient. It measures how well a model accounts for the variability of the label. The root mean square error. It measures a fit using the sum square of prediction error. Mean absolute error. And measure a fit using the absolute value of prediction error. Note, you do not need to know how to calculate this. There are functions and scikit-learn that will calculate them for you. However, if you're interested in understanding the math, we'll go briefly about them in the next slides. Okay, so we'll talk about those each one specifically. So I'm gonna wait till the next slides. Again, you don't need to learn this mathematical part, right? It's gonna be done for you with the tools of scikit-learn. So R2 coefficient, what is it? What does it do? So a measure of how well model accounts for the variability of the label. So that's practically the definition. R2 ranges from 0 to 1 with larger values indicating a better fit. If you get a negative value, your model is really bad. So this is going to be spitting out a value between 0 and 1. So if your value is close to 0, that means it's not a very good prediction. If it's negative, then you're way off. But what you want to do is you want to make sure that your value is within 1, close to 1. Not 1, but not 1. Because then if it's 1, that's an overfit. We can generally say that R2 value of the variation of y is explained by the linear regression model. So example, 75% of the variation in life expectancy is explained by linear regression model. Here's a little more depth on what the mathematical part of it. The sum of the squared residuals. So SS means the sum of squares. So the total error cost function of your model prediction compare on the real value. So we're saying here that 1 minus the sum of the square regression divided by the sum of the squares total, that's going to be your R squared. So that would be practically 1 minus your residual over there. Yeah. So here is one residual. So you have one residual at the top. So you're doing every single, you're adding every single residual on your data, and in the bottom part, you're actually just you're adding you're taking the difference. Sorry, you're adding the difference of the y values between each point in your linear regression. And then on the bottom part, what you're doing is you're adding the difference between each point and the average value of your y. So there's two different things. One is doing the residuals, right? Summing the difference of the residuals. And the other one is doing the difference of the average. So that's going to calculate the R squared. The total sum of the squares, the total error cost function of the model that predicts the exact same value every time, specifically the average of the data. We compare this to the model because it represents a baseline of capturing no variation. So like I said again, this is just a way to measure how well your app prediction was. So again, so the top part is your residual, the sum of your residual divided by the sum of the difference on your point to the average y value. Okay, so the mean. So here is a little bit better to interpret the result. So let's consider this this part right here. So if you have a negative number, that you're way off, right? That's bad. So let's go to the first one. So if you have an R squared value, so that's 1. So in so in this case, your SSR, your sum of squares regression will be 0, right? So our model fits every single data point perfectly. There are 0 residuals. This is a sign of overfitting. So remember, you want to get close to 1 for your R squared, but you don't want it to be 1. If it's equal to 1, you're in trouble. That's overfitting. Now let's do the opposite, right? So let's say that your R squared is 2, and that only happens if your sum of square regression and your sum of square total is equal to each other. That means that you have 1 minus 1. Our model is the exact same as the average model, so it reports that the same value, the average, every time. So this is a sign of underfitting. So you're not fitting well. So that's a bad sign. So you want to be close to 1 but not equal to 1. Another example would be if your value R squared is less than 0. Our model is worse than the average model. It doesn't even capture the average of the data pool. This is a terrible model. Okay, so if you have, when you do your R squared and you calculate something that is less than 0, that means that you have done something wrong. You have to go back. Right, so you want your R squared to be close to 1 but not equal to 1. All right, so the other one would be the root mean square error. So the root mean square error measures the square root of the sum square of a prediction error. So measures the square root of the sum square of the prediction error. We'll see the formula for that one. This is how far your model predictions are from the real numbers. Smaller values of the root mean square error mean a better fit, but the value itself is not meaningful unless it's compared to another model's root mean